Hi, this is Mr. Miller, and today's lesson is on the cell membrane and osmosis. And if you would open up your student note sheet, at the very top, add a text box and write the essential question. How does water move into and out of our cells? And what effect does that have on our cells? The first thing we're going to do is try something called the Smelly Balloon test. So what I'd like you to do is watch the experiment on this YouTube clip. It's about a minute long, and it's a cute little video from a Children's Science Center. But when you're done, answer the two questions on your note sheet. So pause the video and do that, please. Well, hopefully you figured out that in order for the kids to smell those different scent molecules, literally the balloon membrane had to be permeable to some of those molecules. That means the vanilla smell had chemicals that had to pass through the balloon to their nose. Now, how is that similar to what we're about to talk about? Well, we know that molecules have to pass from high concentration to low into a cell. Things like sugar molecules have to go through what's shown here as a cell membrane. Water molecules have to pass in. Oxygen has to go through. Carbon dioxide. So molecules like that have to pass through a membrane, and this lesson's about how they do that, specifically focused on water. Now, water itself can actually be dangerous, and there's a video here. It's a little bit sad, quite honestly, but it's about a woman who died when she entered a radio contest drinking water. So if you would, watch this little video clip and then answer the question, what happened to Jennifer's cells that resulted in her death? So watch that video clip and see if you can answer that in your notes. So once you saw that, you realize that one of these situations occurred. Jennifer drank so much water that she was out of homeostasis. The water concentration was very high in her cells. So which one of these situations applies to Jennifer's case? Did water move into her cells, red blood cells, in which case they popped? The word we use is lysed. Did water move in and out evenly, those cells? Or did water leave the cells and go out into her bloodstream and the cells shriveled up? The word we use for that is plasmolyze. So which do you think they did? The correct answer is her cells lysed. So with too much water in her blood, it was in high concentration outside her cells. Therefore, water, like any other molecule, will diffuse from high to low concentration. So it diffused into her cells and lysed. So what is the science behind it? The science behind this is called osmosis. So make sure you write down this definition and put a star by it. Osmosis is diffusion, but it's diffusion specifically of water molecules. And so like all diffusion, those water molecules diffuse from high concentration to low concentration. But the kicker is they have to diffuse across a membrane. And we call that membrane semi-permeable. Now the word permeable means things can pass through. So if you look at this model here, the blue molecules, or blue dots, represent water molecules that can pass through the holes in this permeable membrane, whereas the larger dissolved stuff, like salts or something, are too big to cross the membrane. So we would say the membrane is permeable to the water, blue dots, but impermeable, or not permeable, to the orange solutes. Now notice when we started out there were more blue dots, therefore more water particles on the left side of the membrane, so there is a concentration gradient and water molecules will diffuse from high concentration to low. We learned about diffusion. The water particles will diffuse both ways across the membrane, but overall the net movement is from left. So if you'll notice here, when we reach equilibrium, water molecules will flow both directions equally. So we say there's no overall change in the number of particles. They're already at equilibrium. So there's no net or overall flow difference. So one of the things you need to learn when you talk about osmosis is what is a solution. So here are a couple definitions you need to have. In the picture of the beaker on the right, we have a solution, which is where at least two substances are evenly mixed together. So if you were to put sugar in water and stir it up, you would have a solution. Soda pop is a solution, and so forth. So when you have a solution, the molecules that are in highest concentration are called a solvent. We usually say it's the liquid that dissolves stuff. And for the living body, water is always the solvent, and therefore we call water the universal solvent. Now a solute is whatever you dissolve in the water, in this case these orange particles. That could be salt, it could be sugar, it could be Kool-Aid, it could be anything that will dissolve in water will be called a solute. Now, in osmosis there are three different cases I'd like to talk about, and they're shown in the notes here, but I'm going to stop here and draw some things that you can draw on your note sheet in Cami. So in the first scenario, we're going to take one cell and expand it to make it look way bigger than it is, and we're going to drop it in some fresh, pure water. Okay, so here's a cell shown here, and we're going to drop that cell in pure water. So in your notes, if you would draw a beaker that's got water in it, and draw one giant cell inside that beaker. Okay, let's suppose that in that particular liquid there are no solutes, so it's 100% water. Now I'm going to give you a number here that is actual number that anybody who works in health field needs to know, and that is that the cells of our body normally have just less than 1% solutes. So that would be a 0.9, just less than 1% solutes inside the cell. Do a little math and figure out how much water is in the cell. Well, every solution is either made of solvent or solute. And so if you have just less than 1%, in fact you might memorize that, 0.9% solutes, then you got 99.1% water. Now, which is higher, 100% water or 99%? And the answer, of course, is 100%. So what you see is that water molecules will always diffuse from high to low, like everything else. So water surrounding this cell moves from 100% concentration to 99.1% concentration. What will happen to that cell? Well, because water's moving in, the cell will swell, and if nothing stops it, it can burst or lyse. And of course, when that happens, cell's dead. All the guts leaks out. Now, the solution here, this 100% water, because it has high water, but it has 0% solutes, so we have a name for it. It's going to be called either hyper or hypotonic. Now, the suffix or the prefixes, hypo means low, hyper means high. If you're hyperactive, you're too active. So, in this case, we look at the water outside and we say, tonic refers to the solute concentration. Since we have low solutes outside the cell compared to the cell, we call this solution hypotonic. So 100% water is a hypotonic solution. Water will always flow into the cells and lyse them. Right? Let's draw a second condition here. Let's suppose this time we drop our cell into a different solution. Let's say the liquid in here has 5% salt. Now if it's got 5% salt, the rest of it's water, so 95% of that solution outside of the cell is water. And let's say that again that inside the cell we had 99% water. Since osmosis is the diffusion of water across a cell membrane or any semi-permeable membrane, we ask ourselves, where is water in highest concentration? Well, 99% is bigger than 95%. So water will move out of the cell by osmosis. Even though there's more volume of water outside the cell, the concentration of water is greater in the cell than out, so water moves out. And here the cell will shrivel up as water leaves it, and that's called plasmolysis. Now, the question is, the liquid that we put this cell into, is it hyper or hypotonic? Well, 5% salt, that's the solute, is greater than 0.9% solutes. So this 5% is called a hypertonic solution. Now you can probably guess what the third scenario is. Isotonic means same solutes. So if the cell and the solution have the same amount of water and the same amount of solutes, then water molecules will move back and forth in equilibrium across the membrane. And that's exactly how you stay alive. In order to maintain homeostasis and to stay alive, your blood must always be exactly isotonic, which means it has 0.9% solutes in it. That number is so important that every doctor, every nurse has to know 0.9% solutes. If you give someone a shot, you better make sure you add enough salt to make it 0.9%. Everything you put in a person's body, inside their bloodstream especially, must be at what we call physiological saline, or 0.9%. The next activity just gives you a little practice. So look at those blood cells and explain what's happening to each one, cell 1, 2, and 3. Hopefully you said in cell 1, since the cell was placed in an isotonic solution, that water is at the same concentration inside and out of the cell, so it comes and goes freely and there is no net movement of water. In cell 2, it was placed in a hypertonic solution, which was very high in solutes, therefore low in water, so water moves from inside the cell to out. And as the water leaves the cell, it shrivels up and plasmolyzes. And likewise, cell 3 was placed in a hypotonic solution. Low solute means high water, so water will diffuse into that particular cell from high to low. So to review, the environment of a cell can be hypertonic, where the environment has higher solutes than the cell, and as a result it has less water, so cells will always lose water in a hypertonic solution. In a hypotonic solution that has a lesser solute concentration than the cell, which means it has more water than the cell, so water will always move into the cell. And isotonic means same, so there's an equal concentration as the cell. If you watch this video, you'll notice these are plant cells. They look kind of boxy, and they've been stained in their cytoplasm a little bit pink, but we added a solution to these plant cells. As you watch the cells, see if you can notice anything occurring. You might notice the cell membranes are shrinking up and pulling away from the walls. Now, what kind of solution would make that happen? Hyper or hypotonic? Well, hopefully you said hypertonic for that last one. Now, these are red blood cells that have been placed in a hypotonic solution. Watch the cells and see what happens to them. You can see this one's starting to have something showing up on the outside. It looks like it might be swelling larger and larger compared to some of the ones above it. Oh, some of these are bursting. Boom, boom. That's called lysis. And that's exactly what happened to Jennifer's cells. So now we can make predictions about what would happen if, say, you pour salt on a slug. The slug's got a lot of liquid on its mucus, and so basically you create a hypertonic solution, and water leaves the slug's cells and kills the slug. What would happen to a saltwater fish if you put it in a freshwater pond? They're well adapted to life in the ocean, which is pretty close to isotonic. When you throw them in fresh water, though, it's a hypotonic solution. Water enters their cells, and they won't blow up, but their cells will lyse and kill the fish. I don't think you'll hear a giant explosion. All right, so let's try a little practice here. And I'm going to caution you, there's one thing I don't like about this particular practice, and that is it acts as if cells have different amounts of water in them, when in fact, any doctor will tell you, anybody in healthcare will tell you, all cells have 99.1% water and 0.9% solutes. However, for the purpose of practicing osmosis, let's assume the amount of water in each cell can vary. So in beaker 1, there's 90% water inside and outside. So the question is that cell isotonic, hypotonic, or hypertonic, and will the cell shrink, grow, or stay the same? So work those 3 problems, come back and check your answers. Okay, so the first beaker, of course, is isotonic, and therefore water moves evenly back and forth. There's no net movement of water into or out of the cell. The second solution had lower solutes than the cell. 30% is lower than 40, so it's a hypotonic solution out here, and that would cause water to move into the cell, and the cell would grow larger, possibly lyse. The final one is a hypertonic solution because there's more solutes in the solution than there is in the cell, and therefore water moves from water's highest to lowest concentration. Okay. The tricky thing about this is osmosis is the movement of water, but the words hyper and hypotonic are describing the solute concentration. Okay, here's what I'd like you to do. Before you go work on the practice problems that are just like this, I'd like you to go back to the video on feeling osmosis and finish figuring out why is it the lettuce was soggy in one solution and crisp in a second solution. So go ahead and finish filling out that activity now that you know a little something about osmosis. And I hope that helps. We'll see you later.